In this video, we move forward on our fluid structure interaction problem at rest by linearizing the equations for small oscillations. We have previously scaled the set of equations in the problem. This is our starting point for this work. The first question to ask is, under what conditions can we linearize the equations? It is a kinematic condition that will provide us with a criterion. Indeed, we have shown that the dimensionless displacement psi in this relation is of order psi0 over L, which is equal to the displacement number d. In the solid, xi is of order d, and this relation indicates that in the fluid, u is also of order d. The condition to be able to consider small oscillations and linearize the equation is therefore to have d small. We will now do this work in the fluid, then in the solid. Let's start with the mass conservation. The velocity is thus decomposed into a stationary part, 0 for a fluid at rest, and a fluctuation of order epsilon. Epsilon is the usual name for a small parameter, but it should be noted that in our case it is strictly equal to d. The pressure is also decomposed into a stationary part p0 and the fluctuation epsilon p', as well as the density. It remains to introduce these quantities into the dimensionless mass conservation equation. Two terms of order epsilon and a term of order epsilon squared appear. By neglecting the last term, we obtain an equation in which the density fluctuation is neglected. It only appears through the pressure fluctuation when used in the state law to express its variation. The presence of the term R0 allows us to take into account a possible variation of spatial density of the fluid in the stationary state. However, it is not relevant to continue to take into account this case because it happens mainly when there are temperature gradients or salinity gradients in water. Since we do not take into account thermal effects or possible chemical effects in our analysis, we can therefore set this term to 1, since the reference density F0 was used to scale the density. For the linearization of momentum conservation, we start from the same decomposition of the field variables in the fluid. After introducing this development, we obtain terms of order 0 up to 3. Let us start by neglecting all terms of order greater than 1. Then, let us notice the term in epsilon r', which allows us to take into account possible hydrostatic force linked to the density fluctuation. However, for the same reason as before, it is reasonable to consider a fluid of constant and homogeneous density. We can now separate the terms of order 0 and order 1, which gives us two equations, one for the stationary reference state and the other for the fluctuations. The zero-order equation is the dimensionless form of a well-known equation. It is the equation that governs the hydrostatic pressure, which is minus z over fd plus a constant. This result will be useful when we need to express the stationary part of the stress tensor in the fluid. Since the zero-order velocity is 0 in the case of a fluid at rest, we will simply have sigma naught equals minus p naught times the unit tensor. Now that the fluid has been treated, let's look at the solid side. To simplify the analysis, we have previously expressed the dynamics in terms of a single eigenmode problem. On the right side appears the product of the fluid modal force and the mass ratio. By introducing Q equal Q0 plus epsilon Q' and separating the order 0 and 1, we obtain an equation that determines the equilibrium position of the oscillator under static forces and the dynamic equation. It remains to linearize the fluid force. Let's take the expression of the projection of the fluid stress on the deformation mode of the solid. We can express it as the projection of a force element on the phi mode. The nonlinearity of this expression is mainly hidden in the fact that the integration surface varies during the oscillation of the structure. d omega is different from d omega naught. The objective of our linearization will be to bring this integral back to d omega naught. During the transformation, the normal to the surface changes from n naught to n. Let us enlarge a small part of this surface and represent it in 3 dimensions. During the transformation, a small surface element centered at position x0 moves to the position x. These two positions are linked by the displacement vector epsilon psi prime. We note ds, the oriented surface element, which in the reference state is ds0. Similarly, the fluid stress is noted df0 in the reference state and df in the current states. df is equal to sigma scalar n. On this notation, the subscript x indicates that df is evaluated in x. The linearization then consists in performing a Taylor expansion of the two quantities of this product in x with respect to the reference position x0. The stress tensor reveals a term of order 0 and two terms of order 1. The first one is the first term of the Taylor expansion of sigma naught. The second one is the fluctuation of the stress at x0. The Taylor expansion of the stress fluctuation gives the term of order 2, which is neglected. The development for the oriented surface element is more complex, but we can appeal to results from tensor algebra or continuum mechanics courses. They show that for the displacement field epsilon psi prime considered here, an oriented surface element can be expressed to order 1 as follows. We see that the oriented surface element is equal to the surface element in the reference state ds0 at x0, plus two terms of order 1 involving the divergence and the gradient of the displacement field. By taking the product of these two expansions and keeping only the term of order 0 and 1, we obtain this expression, which involves only fields expressed in the reference position x0. Let us now particularize df in the case of a single-mode dynamics in a hydrostatic pressure field P0 and project this on the considered deformation mode. The fluid force then takes this expression, which will be very useful to us because it only involves integrals on the interface in the reference state d omega naught and fields defined at x0 in the reference fluid domain. The motion of the interface, which is a source of great complexity, is no longer involved in this linearized form of the fluid force. We distinguish one term at order 0 and several terms at order 1, which we will describe in more detail in the following videos. In our general fluid structure interaction problem, we have succeeded in implementing the scaling in the previous video, as well as the linearization of this equation in the present video. Let's have a look at the program that is waiting for us now. Now that we have implemented the linearization of the equation, we will be able to analyze different effects of the fluid. Focusing on the stationary terms of the fluid force, we will first show hydrostatic effects. Then, neglecting viscous and compressibility effects, we will focus on the stress fluctuation to highlight inertial effects. In the next 3 videos, we will make different approximations and highlight the influence of free surface dynamics on the dynamics of the structure, the effects of viscosity, and the influence of acoustic radiation on the dynamics of a structure. See you soon.